mic will help, I hope.
It's a tutorial.
Yes, it's a tutorial, so it's more relaxed. So the idea is to somehow explain some stuff, like perform some actual computations to check that things work in examples. So basically things that I didn't do in the lectures. So the thing that I want to talk about first, so in the definition of a compact quantum group, we had this commultiplication and this cancellation rules, and I mentioned that in the classical case, for a compact semigroup, these cancellation rules imply that we actually have a group. So I wanted maybe to explain it a bit. I mean, I said that it would be an exercise, but I think it's not a very easy exercise, so maybe I should actually give you the explanation. So assume that G compact semigroup with cancellation, so both left and right, then G is a group. So we'll do it in two steps. I mean, we have to do two things. We have to find a unit first, and then we have to show that every element is invertible. Okay, so we need a definition of an ideal. So a subset in a semigroup is called an ideal. Well, if Gi is a subset of I and Ig is a subset of I, for each G in G. And we actually only use this notion in the commutative case, so I mean it will be actually one condition. So now let's start with an element H. In G, and consider H, which will be the sub-semigroup generated by H. Probably the closed sub-semigroup. Generated by this element H. Okay, so we have a compact abelian semigroup, and we want to use it somehow, so we'll find the unit inside. So if I1 and I2 are ideals, then their intersection contains the product of the ideals. Right, because I mean I2 multiplied by anything from I1 is inside I2 by the ideal property and also the other thing, right? So it's also contained in I1. So what follows is that if you have a finite family of ideals, then the intersection is non-empty. And then by compactness, it means that the intersection of all of them is non-empty, right? Because there's a family of compact subsets with finite intersection properties. So this is here the place where we use compactness. So by compactness, the intersection of ideals so we kind of get a minimal ideal. So we get this IH, the thing we call IH as the intersection.
ideals to be closed.
Yeah, we do everything closed. Sorry, and non-empty, yeah. So non-trivial, yes. Yeah, of course. Yeah. So non-empty closed ideals, yes. Okay, so now we have that H times IH, like not even like K times IH for any K in say IH. So one is the inclusion, the left side is smaller than the right side, the right hand side by the ideal property, but it cannot be strictly smaller because I mean IH was this intersection, and this is also an ideal, so they have to be equal. And K is inside, so it means that there exists E in IH such that K times E is equal to K. Right, because the K is a product of K by something from IH. Okay, so now we somehow return to the original group, semi-group, not yet a group, for any G in G, we get KEG is equal to KG, and now by cancellation we get that EG is equal to G. This is where we use the cancellation. Okay, so our semi-group admits a left unit using the same argument but on the other side, and using the other cancellation law, we obtain a right unit, and then if you have a semi-group that has a left unit and the right unit, they actually have to be the same, and they are a unit. And then to get inverses, I mean, you do a similar thing. So for inverses, we look at H, IH is equal to IH. Then, because E belongs to IH, right? I mean, it's an element of IH. We get some sort of K in I. So we put E on the right hand side here. It means that there is a K such that H times K is equal to E. So H has a right inverse, then the same argument shows that it has a left inverse, and it means that it has an inverse. And we started from an arbitrary element H, and for each H we can repeat this argument. It shows that we have a unit and that each element is invertible, so we get a group. Yes, the question.
H belongs to the closed ideal plus subset.
Yeah, H is the closest semigroup generated by H, yes.
Just the same.
Yeah.
So why does it get non-trivial frequency?
Well, the whole thing is an ideal, right?
You do it inside H.
Inside H. So there are ideals inside H. So the whole H is an ideal inside H, right? Yeah.
How do we know that H is in
That's actually somehow that was not necessary here. It's K in H is okay. Yeah, sorry, yeah, that's correct. Then we use something, when we applied it for K in IH to somehow have it on the both sides, but yeah, this equality does not need it.
So why do you actually need to go to this closed semi-group generated if you just start from ideals?
Yes.
Like where is it?
You want to be committed.
I think you want to be committed. Somehow it makes things simpler.
No, you just have to do it.
Yeah.
If you want to use the argument below.
Yeah, probably.
Okay, yeah.
You have to be, that's true. Yeah. You need it on both sides, so that's why you need a billion. Oh yeah, it's a bit. Yeah, so it's for me it's kind of very tricky. I mean, you can follow the argument, and it's okay, but somehow it seems a bit random. But magically, somehow the generalization of this approach to compact groups, I mean, it somehow gives us very nice theory. So.
I can make a comment. It's kind of not so random because you can just think that you just need to build an idempotent.
Yeah, I guess so. Yeah, that's
the
true.
idea is that you just get one element, you multiply it by itself many times.
That's true.
You have compactness. So
Yeah, so somehow you cannot do the usual trick that we want, which is to take, the averages, right, of the power. So we have to do that.
So it's really like the idempotent is kind of like of powers of H, right?
Yeah,
Which is this way
kind of.
So it's realized in this, I guess.
we've seen. So Mateusz proof this idempotent belongs to the semi-group generated by H.
Yeah.
It comes from this.
Yeah, exactly.
Yeah. Okay, so that was a bit abstract, but a good validation of the theory that it reduces to the classical theory. Okay, so then there is this other thing that I wanted to discuss is the definition of the version of the matrix compact quantum groups, right? We assume that we have a unitary matrix whose coefficients generate the system algebra, and we had this assumption that the matrix formed by the adjoints is also invertible. And yeah, it's important for the theory, but there's a natural question whether this is automatic. And the answer is no. And the counterexample I will give you is somehow the exact opposite of what Gemma did in her lecture when she gave an example that the transpose map is not completely positive. So the example is you have this matrix. So you have a 4x4 matrix, which is unitary because it's a permutation matrix. But then you view it as 2x2 matrix with entries that are 2x2 matrices, right? So like you view this as this block decomposition. And then if you apply this star operation to each block separately, then what you get is this matrix. You get here nothing happens. Here you get one here, you get one here, you get one here, right? And then the star operation is exactly like the transpose because the matrix is real, so it's the exact same example somehow, but somehow we go the other way, right? This is a positive matrix now, but it's not invertible because you can see that it has a huge kernel. So yeah, at least we know already in the finite dimensional setting, like very small, this assumption is not automatic. Yes. Yeah, that's my U. That's my U, which is specifically I write is like in M2 matrices with entries coming from M2, and this is this UC in this case, which is very non-invertible, quite horrible actually. It's a nice matrix. It's like with respect to invertibility, it's horrible. Like, as a matrix, otherwise, it's quite nice. Okay, so this is the other thing that we want to discuss somehow, that this is really a necessary assumption. The third thing, somehow by popular demand, I heard someone wanted to actually see it. So I mentioned that in these compact matrix quantum groups, you always define this co-multiplication by somehow mimicking the matrix multiplication. And I said that co-associativity of this is automatic, but we didn't check in any example that you can actually define this star homomorphism. So that's what I wanted to do in the case of the UN plus. On UN plus. Okay, so we call that this is the C-star algebra generated by elements Uij, such that the matrix U formed by these Uij's is unitary. Well, in Mn of the C-star algebra. UC, which is formed by the taking the stars, is also unitary. I will maybe not do the whole computation, but at least part of it. So let's write properly what it means for it to be a unitary, just to have an algebraic formula. So the ijth entry of Uij, is the U star of ik U kj, and the U star of ik is uki star, and here we have ukj, and we want this sum to be delta ij 1, and then the other condition for unitarity here is that you have the sum of uik ujk star is also delta ij times the unit, and then we said that we want delta of Uij to be sum of Uij, sorry, Uik Ukj, and let's call this thing, I don't know, Vij. So one thing that we want to check is that the matrix formed by these Vij's is unitary. Okay? So we want to check, right? Because then this is the C of UN plus is like a universal object generated by Uij such that they satisfy these two conditions. So if we find any other realization that satisfies these two conditions, it means that we have a star homomorphism from this C-star algebra to the other one. So this is what we want to do, right? We check that this matrix formed by Vij satisfies generating relations, defining relations, sorry. Okay, so let's maybe try to do this first condition. So yes?
Please again why you want Vij also to be sorry?
So we can define a homomorphism from this universal algebra to some other algebra, if and only if the images of these things satisfy the defining relations of this object. This is just the definition of the universal property. So we want, basically these equations, and similar ones for UC satisfied by Vij's in place of Uij's. Okay, so we have this, for example, Vki star, Vkj. This is gonna be difficult. Okay, sorry, but I think it's gonna be okay. So we have, so Vki is Vkt tensor Vi star.
You.
U, sorry. So
You
close.
want one more sound outside of it.
Yes, not, yeah. Sum over K, this is sum over P, sum over Q. This is J, so U, K, Q, sorry, U, Q, J. Okay, so now we get a long sum over three indices, K, P, K, and we have U, K, P star, U, K, Q, tensor UPI star, UKJ. Okay, that's the expression. So now if we first sum over K, K doesn't appear here, so we can just focus on the first leg of this tensor. And then you see that this is delta PQ times identity, right? So this thing, when we do the sum over K, it gives delta PQ times 1. Right? This is the original defining relation of U. Now we already summed over K, so we have the sum over PQ left. It's delta PQ1 tensor UPI star UKJ. Okay, so delta PQ just means that P and Q are the same, so just equate these indices. Okay, so this sum is actually sum over a single index, 1 tensor UPI star UJ. This once again is the relation that we know. This is just delta ij times the unit. So this is the delta ij times the unit, this is the unit in this tensor product algebra into which we map. So we check that this relation works. Then for this relation, I will not write it down because it's exactly the same. Like the same computation, but you have the stars on the other side, and then you still first sum over one index, you get identity times some delta, then you perform the other sum and you get the same thing. And for the other condition, it's also the same. You get some sort of relation of roughly the same form, and you just check that when you define this delta like that, it also satisfies these equalities. So this sort of covers the example of UN plus. And for example, Sn plus had this extra condition that the Uij's, the entries were supposed to be projections, right? So then this is also, so then the only extra thing you have to check that you will get projections here, but this is also easy to check because somehow you multiply on different, on separate legs and it works. For On plus there was another condition that somehow you have self-adjointness. This is also easy to check, maybe even easier. So basically, these basic examples that we had can be handled in this way. So it's just a mildly annoying algebraic computation. I don't know. So this is what I wanted to cover. Mike, do you want to talk about something else today? Of course, if there are any questions in general, then we're happy to.
Maybe related to this last computation. So if you just have the conditions, right, the necessary ones for calculating one, not in addition, so if UC is just convertible.
Yeah.
I guess that doesn't work. Right?
Just like
just
there's no.
Theory, UC is invertible.
Yeah, there's no general.
Some C-star algebra, but is delta well defined in that case?
What do you see, algebra? It's not.
Is that
It's U is
use unitary is not enough to get out?
For some of them, right?
But how do you involve this fact that you see is invertible?
Yeah, that's somehow. This is not a. Yeah, that's true. It's somehow you would need to do like sometimes they do in algebraic geometry, like they introduce an extra variable, but then this extra variable would probably be like an unbounded operator in a way.
Okay.
So
So that doesn't
that's a bit tricky, yeah. Somehow you would do like a projective version, like with the determinant, right? But then it's unbounded. So yeah. I mean, you can sometimes try generating C-stars by unbounded operators, but yeah, probably will not lead to a compact one.
But maybe you have to make a comment on what you said. So what you can do, you can say, well, this is, I think, Mike mentioned this, that this you see, okay? Once you know that this comes from a quantum group,
Yeah.
then you know it's similar to a unit.
Yes.
Right? This is exactly this unitarizability. So you can fix the similarity,
Yeah.
and then you can look at the class, the quantum group given by this. Okay,
Yeah.
U is unitary, and UC is similar to unitary phi at this particular.
So this is So this is something that we haven't really covered, but this is there's a version of UN plus called UF plus where you basically fix this similarity where some similarity of UC is unitary, and then for fixed F you can do that.
And then by abstract nonsense, every compact matrix quantum group is a quotient of one of these.
Yeah, this is like a
That's the
universal.
statement.
Mm-hmm.
I guess one thing we could talk about is why compact matrix quantum actually compact quantum groups, why they cancel. I could. Or I don't know, anybody else?
Maybe one other question related to that. So, were you planning to cover like you have a representation that you see is invertible?
I stated I can comment on that.
I don't know if this is like useful.
Yeah, I mean, there's actually a formula for the inverse, validating formula. So there was this construction from last time, which was if you have a unitary representation. Okay, so this is just a unitary matrix which behaves nicely with respect to the coproducts. Okay, we form this contragradient thing. Okay, so this is so if I write U concretely as a unitary matrix with entries Uij, UC is Uij star, which is usually interpreted as something that wants to be a representation of the conjugate space. Okay. So in a basis-free way, you can really write UC as the transpose tensor identity of U inverse. Or U star in the case where U is unitary. Okay. So this is the conjugate or contragradient representation. So if you apply delta to the entries of this matrix, the right formula holds because delta commutes with the involution. So that's an easy thing. The hard thing that we don't easily see is whether this is still an invertible thing. So that's what you need for a representation. And the claim is that UC is invertible. And there's actually a formula for the inverse. I think I wrote it down here. Yeah. Yes. So I'm going to form this matrix Q. there's actually a left version and a right version, and they appear sort of naturally when doing the modular theory of the Haar state, which maybe we'll hear about in the next lecture. But I'll just write down the one I need. Q is, what I do is I take UC, and I look at UC times UC star. UC star, of course, is just, if you think about what you're doing here, the star of this is just the transpose of U. This is equal to UC times U transpose. The entry lies transpose of the matrix. Okay, and so once again, I mean, this is of course a positive semi-definite matrix. I'm taking a positive semi-definite operator that I don't know is invertible, and I'm slicing it by a state, and so I'm going to keep positive. So this is bigger than or equal to 0 in B of H R. But the hard calculation is that it's actually strictly positive. So this is actually invertible. Okay. And I won't go into the details of how one checks this, but it can be shown that, okay, and you can reduce to the case where U is an irreducible representation. It's really a highly non-trivial fact to check that Q is not only positive semi-definite, but actually an invertible positive. But
maybe a silly question.
Yeah.
So you wrote that U is acting on H.
yeah,
And then UC is just given by Uij star.
yeah.
How does it act on H bar? What's happening there?
Well, I mean, you can also, I guess, regard it as acting on H as well, right? It doesn't. Yeah, I mean, it's a choice being made. Yeah. So normally, I guess, when you define the contragradient representation, you can define it for non-unitary representations, and the idea is you're really looking at the analog of the dual representation, right? So when I act by a group on a vector space, I can, let's say, look at the dual space if it's finite dimensional, and I consider essentially the transposed map, right? So the way you should think about UC, so if this is actually a representation of a group, UC of G is, this should be, if H is not even a Hilbert space, just a finite dimensional vector space, right? You're going to act on the dual, and UC of G, how does it act? UC of G is acting on a functional, and that's determined by how it acts on the vector, and the formula is the usual one. You apply the functional to U of G inverse of the vector, right? So in reality, I mean, if you think about what this is like, the contragradient is actually the transpose. So the transpose of U of G inverse. So for a Hilbert space, of course, the dual you naturally identify with the conjugate space. So this is where this is coming from. But as Adam said, I mean, one can just interpret this thing right here, as sort of living on the same H. Yes, yeah, you're interpreting it with respect to the dual basis. That's correct. Yeah.
Once you choose the basis,
Yeah.
it's the same space.
Yeah, yeah. Once you choose the basis, it's the same space. I guess that's the way to. Yeah. So Q is invertible, and then yeah, the miracle is this Q basically gives you the formula for the inverse, and yeah, so. U C inverse is Q U C star Q inverse. And yeah, the way one kind of sort of checks this is you form something like this Q matrix, then yes, I'm going to let's gets. I mean, the sort of part of the argument is using this averaging trick. So you're averaging UU star, okay? And what this will give you is that basically U C Q U C star is equal to Q. You get equations like this. And similarly, if you form another Q, a sort of opposite version of Q where I put the UC star on the left-hand side, you'll also get for the other Q, UC star Q, the other Q, UC equals that other Q. All right, and so you get sort of two candidates for Q and the other Q, and it turns out those two Qs are actually inverses of each other.
Sorry, how do you get this?
So it's, right, so you use the, right, so you write this as it's the same calculation I did yesterday actually, so it's like 1 tensor H, UC star, star. So write it this way. And then this is like identity, tensor H, tensor identity, something like this. And now I use leg numbering. And this is like UC, UC, UC star, UC star. Okay, and now this is going to be like UC1, 3. Maybe I want, sorry? Maybe I try this. I don't know. There's some trick that works. I know that. Yeah. Yes, this would be 2. 1, 3, 1, 2. So I write it this way. And then, this is basically, this whole thing is identity tensor delta of UC star. So identity tensor H of identity tensor delta of UC star. Well, H absorbs the delta, and what you're left with is the Q that you start with. So you get a formula like this that if you knew Q UC was invertible, then you get this. Okay. Again, the invertibility of Q is the hard part. I do not remember right now off the top of my head how one checks this, but my memory serves me correctly. It's kind of non-trivial. What's that? Yeah, perhaps. But Mateusz will. lecture. Yeah. Okay. Yeah. I guess we're out of time, so we'll stop here.